Hi there, we present you our work, Multi-Space Neural Radiance Fields. Neural Radiance Fields, or NeRF, achieves significant performance in lower view sensor size, but fails to render high-quality reflection and refraction when camera moves around such objects. We construct two toy sensors to analyze the cause of the failure and propose a very simple assumption. Based on our analysis and assumption, we propose the multi-space neural radiance fields in the form of a lightweight module, which produces multiple pairs of densities and features instead of one to represent the multiple subspaces. We also construct a new benchmark with complex reflection and refraction to evaluate NeRF-based methods. Our method outperforms the existing methods by a large margin, both quantitatively and qualitatively. We will further discuss the details of our paper. NeRF represents the same as the radiance fields model from traditional computer graphics, where each point in the space has a density property and a view-dependent color, and NeRF utilizes simple MRPs to fit the same. Although NeRF-based methods achieve SOTA performance in non-lambda materials, they fail to render high-quality reflection and refraction when camera moves around such objects. The virtual images caused by the mirrors can only be seen in a few views, and in other views, they are invisible. We guess that the missing virtual images confuse the simple network by violating the multi-view consistency. To analyze the cause of the failure, we constructed two 360-degree toy sensors using Blender, in one of which we place a mirrored plant behind the mirror, and we train to vanilla NeRF. As can be seen, by turning the virtual images into multi-view consistent, the NeRF fits the virtual images well and render high-quality images. And when multi-view consistency is violated, NeRF tends to treat reflections as textures to avoid violation. Based on our analysis, there are three ways to extend the NeRF-based method. The direct one is to enhance the shading ability like RefNeRF. By introducing foam shading model, it achieves great performance on specular materials, but the shading of reflections are very different. Therefore, it fails to render mirrors. Another way is to enhance the sampling strategy or enhance the recasting direction. Iconophiles achieves satisfying performance by introducing index of refraction to guide the redirection, but it is still under exploration and not suitable for reflections. What's most related is NeRF-RAN. This method improves the performance in forward-facing sense with mirrors. They propose three restricted assumptions to decompose the rays into transmission and reflectance, but the assumption fails to generalize in 360-degree sense. We propose a very simple and more general assumption. When reflection and refraction exists, our real spaces can be decomposed into multiple subspaces. Based on our assumption, we construct a multi-space module, which only modifies the output part to produce the multiple pairs of densities and features instead of one, to represent the multiple subspaces. To leverage the modeling ability, we use feature fields instead of radiance fields, and use two layered MLPs to decode RGB maps and pixel-wise weight maps from feature maps. Then, we perform weighted sum to get the final rendering. As we will only modify the output part, this module is compatible with most NeRF-based methods. We also investigate the existing datasets for NeRF and find that most materials are non-Lambda. There lacks a dataset containing complex reflection and refraction with large camera motions. Therefore, we construct a 360-degree dataset containing complex reflection and refraction. We use the open-source software Blender to construct 25 scenes with camera moving around the central objects. each having 100 training wheels, 10 validation wheels, and 10 testing wheels. We also capture 7 scenes using camera, each scene consisting of common objects and mirror-like surfaces, and following the dataset convention of NERF. We conduct plenty of experiments on our dataset and the RFFR dataset from NERF, which indicates our methods outperform existing methods by a large margin, especially the MapNerf 360 experiments. We improve the PSNR by 3.46 dB with 0.5% extra parameters. Here are more visual comparisons. More information is available at our project page. Thank you.